today we're going to talk about polynomials, and I'm going to break this up over 4 different videos, the first one of which is properties of exponents. So we're going to look at that right now. I'm going to be mentioning several rules, but you don't necessarily need to know the names of the rules as long as you can use what they are and understand the meaning behind them. So the first one is the product rule, and this is a to the m power times a to the n power equals a to the m plus n power. This is called a base, and the m and n are exponents. And if you're multiplying 2 powers and they have the same base, you can just combine them. The reason for this, and I'll just show you a simple example, is if you have something like x to the 3rd power times x to the 2nd power, you can think about what these mean. X to the 3rd means x times x times x, and x squared means x times x. And then if you're multiplying those together, then you actually have x times x times x times x times x, which is x to the 5th power. So this is just this rule kind of shortcuts that. So there's logic behind it, but this shortcuts it, so you can just add those together. Another example of this would just be, just to show you here quickly, you have something like x to the 7th times x to the 9th. We can just write this as x to the 16th, again adding those exponents. So that is the product rule. And we also have the power of a power rule, and this can be written as, I'm going to erase that there. This can be written as a to the m power raised to the nth power, and this is a to the m times n power. So this is called power of a power rule. Again, you don't necessarily need to know that, but if you have a power raised to a power, you multiply the exponents. And a simple example of this would be if you have y to the 7th raised to the 2nd power, this would be y to the 14th power. Again, y to the 7th, there would be 7 y's multiplied, and that's y to the 7th. And then if you're squaring that, that means times itself, so you're multiplying it by another set of 7 y's. So this in total would be 14 y's, so y to the 14th power. So that's why that works. If you forget, you can actually kind of use this logic to figure it out. All right, so that's the first 2 rules. And we're going to end up combining these as we go, but I just want to get these rules out of the way as they are initially. So then we have the power rule, which states that if you have the product, or you might hear this as the power of a product rule, you have a product raised to a power. You just take that power and apply it to both of those. So a to the m times b to the m. This, I think, is a little bit more intuitive than the others, that you would apply that. But an example of this would be like 2x to the 3rd power. This means 2x times 2x times 2x. If we think about what exponents mean, to the 3rd power means multiplied by itself 3 times. And then if we multiply that, we get 2 times 2 times 2, which is 2 to the 3rd power. And I'm just going to write it like that just to illustrate, again, this property. And then x times x would be x to the 3rd power. And by the way, I can do that. I can rearrange this and make it 2 times 2 times 2 times x times x times x by the commutative property of multiplication. And then 2 to the 3rd power is 8x cubed. So we get 8x cubed as our answer. So that's the power rule. Then we have the quotient rule, which is a to the m power over a to the n power. And if you have this, we just take this difference of those exponents, a to the m minus n. So an example of this would be, just draw a little squiggly here to separate this. So if we have 2 to the 8th power over 2 to the 4th power, this is really just 2 to the 8 minus 4th power, which is 2 to the 4th power. And then I can actually evaluate that. 2 to the 4th power would be 2 times 2 times 2 times 2, which is 16. So we won't always be able to evaluate them. In general, if you had something like 2 to the 15th power, you can just write it as 2 to the 15th power. But just if you're in ALEX or looking at different problems, just keep in mind whatever the instructions are asking you to do. Okay, I'm going to give you some more examples of that in a little bit too. But let me get to some of the other properties. All right, we've got the power of a quotient rule. This is kind of like the power of a product rule, but quotient, meaning division, and we are just applying that power on the outside to the numerator and the denominator. So it's a to the m over b to the m power. So if you had something like x over 2 to the third power, we would take x to the third power over 2 to the third power, which we could simplify to the third power is 8. So that's the power of a quotient rule. And then we have 0 exponent. This is an easy one. I like this one. It's easy to remember, and that is anything raised to the 0 power is 1. It doesn't matter what it is. You could have 2x to the second power, y to the 16th power, z to the 100th power. And if you raise all of that to the 0 power, the whole thing is just 1. So likewise, you might have a problem like this. If you had 2x to the 0, notice the difference between these. This one, the 0 is on the outside of the parentheses. Everything is being raised to that 0 power, so the entire expression is 1. On this one, only the x is actually being raised to that power. It's like 2 times x to the 0 power. So this is like 2 times 1, which is 2. So just that's an important thing to note there, is that the 0, you want to consider what that base actually is. Here the base for the exponent is all of this, and here the base is only the x. Okay, so the only other one is negative exponents. This tends to be the trickiest of them, but it is, so if you have a to the negative m, it's equal to 1 over a to the mth power. So if you have a negative exponent, you basically take the reciprocal of it and drop the negative. So that's the kind of a two-step thing there. Take the reciprocal and drop the negative. So an example of this would be if you have 2x to the negative 2. Notice again, this goes back to what the base actually is. In this case, the base is the x, not the 2, but the x. So the 2 is going to stay out here, and the x is what drops to that denominator. And then you can drop that negative. So you take the reciprocal of the base and drop the negative. I can also condense this. This 2 is understood to be over 1, so I can make that 2 over x squared. And I'm going to discuss like kind of some shortcuts and tricks to this as we look at some more involved problems. Those are all of the properties in a nutshell. So I'm going to show you some examples that combine all of the properties together. So the first example we have is 4x squared times 2x to the third power. Okay, so generally, like when you think of order of operations, you think of parentheses. With these, in this case, you would want to apply the power to this parentheses. That's the only thing you can do at this point. And then we will be able to take what we get from this and combine it with that using our properties. So the first thing I want to do is apply that power. That is the power of a product rule. So I'm going to apply that power to that base. So 2 to the third power, which is 8, and x to the third power, which is just x to the third power. And now I have the product rule, where I can just add these two exponents. If you remember that, that was the very first one that I showed you. Also, again, commutative property says that I can take this 4 times 8, which is 32. I can go ahead and treat that out here, and then x squared times x cubed. Adding those exponents will give me x to the 5th. So I have 32x to the 5th as our answer. Here's another example that combines some properties. All right, on this one I have a power of a product, but notice that when I'm taking this power, I'm also going to have a power of a power, so I'm going to treat that here. So the first thing I'm going to do is take 3 to the third power, which is 27, and if you don't know that right offhand, you can use a calculator, but you can also think of it as 3 times 3 is 9, times 3 is 27. And then x squared to the third power, this is what, I'm just going to write this stuff out. You may not need to do this, but just to kind of show you again what we're doing, we're taking each of these raised to the third power, and then this is a power to a power rule. So we can multiply those exponents. Power to a power, we multiply the exponents. That was the second rule that I showed you. Okay, so there's a couple. Leave that up there for a second. All right, so now here's another example. 2x to the 0, y to the third, times 3x y squared. This one involves a zero exponent, so the first thing that I do if I see a zero exponent is I just change whatever that base to the 0 power is to a 1, because anything to the 0 power is 1. So I'm just going to get rid of that, and that's going to become 2 times 1, which is just 2, y to the third times 3x y squared. And then we can, again, rearrange the commutative properties so that we can take 2 times 3 is 6. Y cubed times y squared, that's the product property. We add the exponents. So that's going to give us y to the fifth. And then we have this x here, and there's only one of those, so I can just bring that down. These can be written in a different order. It could be 6xy to the fifth. That would be fine as well. Okay, how about 4x squared over 2x? This is the quotient rule. First of all, you see this 4 over 2, that reduces what I would do with fractions is just think of it as reducing the fractions. So 2 goes into 2 once and then 4 twice. And then this x squared over x, you would subtract the exponents. This is understood to have a 1 exponent. If you don't see anything there, it's understood to be a 1. And the quotient rule says that we subtract those. So it would be x to the 2 minus 1, or just x to the first power. So this just reduces to, I'm going to write it as like this. 2 over 1 is just 2, and then what we're doing is the quotient here is x to the 2 minus 1 is the quotient rule, and that's just going to give us 2x to the first power, or 2x. I'll show you another one of those. Those can get a little bit tricky when you have a lot going, more than one variable, for example, in those. So I'll show you some more of those. Actually, here is a good example of that. We have 2x squared to the second power over 4x. All right, we have a couple of things going on here. We have the power of a product, and then we're going to have a power of a power, and then we have the quotient rule as well. So 2 to the second power is 4. X squared to the second power, we multiply the exponents when you have power to a power, so that's x to the fourth. And then down here, 4x. So these 4's are going to cancel out. 4 divided by 4 is just 1. And then x to the fourth, this is going to leave us with x to the fourth minus 1. Again, that's understood to have a 1 exponent. And then that will give us x to the third power. All right, and even a little bit more involved than that. We have 6x cubed y squared times 2x y to the third power, all raised to the second power, divided by 2x squared y to the second power. Okay, there is a lot going on here. You have several different options as to how you want to address this one. The first thing that we need to do, though, and I mentioned this in a previous problem, is that when we have that power on the outside, there will be one exception to this, but generally, which I'll get to later, but generally if you have this power of a power of a product, you want to go ahead and apply that. So I'm going to do that first. So I'm going to leave that 6x cubed y squared alone, and then I'm going to go ahead and apply this. So 2 to the second power would be 4, x to the second power would be x to the second power, y to the third power raised to the second power, we multiply those exponents, so that will be y to the sixth. And in the denominator, if I apply that 2 to the second power, again is 4, x squared to the second power, multiply the exponents, that's x to the fourth, and then y to the second power is y squared. Okay, what I'm going to do now, and there is more than one way to do this, you will see that there's a common factor of 4's. Because that is multiplication, everything's multiplied, those are common factors. So I'm going to go ahead and cancel those. If that didn't work in this case, you would just go ahead and multiply that and then simplify if you could with the denominator. But in this one, I can actually just go ahead and factor out or cancel out that common factor. Okay, now I'm going to combine this numerator. So we're going to get 6 and then x cubed times x squared. We add those exponents because, again, this is a product. So we add the exponents. So x to the fifth, and then y squared times y to the sixth. So notice I'm treating the same bases together. So I kind of treat the coefficients, and then I treat the x's, and then I treat the y's. And if I had more than that, I would keep doing that. But y squared times y to the sixth, we add those exponents again, so that's y to the eighth. All over, let me draw a little line here so you don't get those mixed up. And then down here, x to the fourth, y to the second. All right, we have drastically reduced the length of this problem. So now we need to do the quotient rule. So we have more than one variable involved here. We have the x and the y. We've already dealt with that 4, so that makes that a little bit easier, but if there was a coefficient down here, we would just want to reduce that, simplify it if we could. All right, so what we're going to do is we are going to write this as 6, and then I'm going to treat this, and again, you don't have to do this, but I'm just trying to illustrate. This is one way, if you kind of find that you're getting confused as to what goes where, you can kind of break it up, because it's just multiplication, and you multiply straight across numerators, straight across denominators. 6 is understood to be over 1 in this case. So I just write that as 6 over 1, and then write the x's and then the y's, and then you can kind of see that quotient rule a little bit more easily, where you subtract those exponents. So this is going to be 6x to the 1, because we're subtracting the exponents, and then y to the 6th, again, because we are subtracting those exponents. And that is the answer to that problem. Okay, that's about as involved as I get until you get to the negative exponents, and that's what can be a little bit tricky when you kind of bring that in with all of the other rules. So, let's see, we've got 3x to the negative 2 times y times x to the 6th y to the negative 4th. Okay, so we have a few negatives, but also notice that I have a product here, so there's a couple of different things I could do. I could go ahead and treat the negatives, take the reciprocal of the base that has the negative, but in this case, I'm going to go ahead and treat, because I have the product rule, I'm going to go ahead and combine the x's and combine the y's, because I might find that it's actually easier. What if I end up with all positives again? Then I wouldn't have to deal with the negatives at all. That doesn't quite work here, but it does with the x's. So we have 3, and then x to the negative 2, again, products, we're going to add those exponents. Negative 2 and 6 is a positive 4. And then the y to the first, again, that's understood to be the first power, times y to the negative 4. Adding those exponents will get y to the negative 3. So we do have a negative exponent. Your instructions when you have a problem like this will generally ask you to write the problem without any negative exponents. We don't like the negative exponents. So we're going to want to take the reciprocal of that base. Only the y is raised to a negative. So we take care of that by dropping it to the denominator. Now I mentioned that there's kind of a trick to this. When you take the reciprocal, you're really just, if it was in the denominator, it goes to the numerator. If it was in the numerator, it goes to the denominator. So that's kind of how we're treating this. So instead of looking at this, we could break this up as like 3 times x to the 4th times y to the negative 3rd, and then make that a 1 over y to the 1 over y to the 3rd, and go that route. But if you just kind of think of it as when you take the reciprocal, it just drops. So a side note on that, if you had something like 1/3 to the negative 1 power, you would just take the reciprocal of this, which would be 3 over 1, to the first power, which is just 3. So if it's in the denominator, you can flip it to the numerator and vice versa. All right, I'm going to show you one more example of this, and then we will be done with properties of exponents. All right, so we've got 2a squared b cubed c to the negative 6 times negative 5ab cubed over 3a squared b to the negative 1 raised to the negative 3 times 4a squared. All right, this has a lot going on. Notice that there is a negative out front of this 5. That is not the same as having a negative exponent. That is the negative coefficient. So we do not take the reciprocal of that 5. We don't do anything like that. We just multiply it as we have multiplied our other coefficients. So I'm actually going to go ahead and do that in this numerator. I'm going to simplify this as much as I can. I'm going to take 2 times negative 5, which is negative 10. A squared times an a. Notice again, this is multiplication all the way across. So this is just the product rule where we add those exponents. So a squared times a would be a cubed. B cubed times b cubed, add the exponents, we get b to the 6th. And then I have this c to the negative 6 that I'll just leave right there because there is no other c. Down here, I see that this whole thing is raised to the negative 3rd. The base for this negative exponent is this entire thing. So the easiest way to deal with this is actually to just go ahead and take the reciprocal of that base, which means if it's in the denominator, which it is, flip it to the numerator. So I am going to go ahead and bring this whole thing up here, 3a squared, b to the negative 1. Now that negative I'm not addressing yet, so that stays where it is. It's this negative that I'm dealing with. So because I took the reciprocal of this base, that negative is going to drop now. So that's a positive 3. All right, you don't have to do that. You could go ahead and apply that to everything down here. It just makes it a little bit messier. So there is more than one way to do this. But so I'm going to flip that to the numerator. That took care of this for now. And then I'm left with this 4a squared down in the denominator. Okay, so what I'm going to do now is I'm going to apply that power up here to everything. So I have negative 10. Just leave that alone. All right, so 3 to the third power is 27. A squared to the third power is multiplied, so we get a to the 6th. B to the negative 1 to the third power is b to the negative 3rd. Over 4a squared. And now I do see that I have some negative exponents remaining. There are a few things that I can do along with that. I can take the negative 10 times the 27. I can take the a cubed times the a to the 6th, the b to the 6th, and the b to the 3rd. So that will actually take care of that negative right here, but this one we'll have to deal with. For space, so that you can see this, I'm actually going to pull this up here. My camera's a little wonky today. Okay, so I'm going to take negative 10 times 27, which is negative 270. And then I've got okay, sorry, I'm losing my spot here. Okay, so negative 270, and then a cubed times a to the 6th. We're going to add those exponents. We get a to the 9th. And then b to the 6th times b to the negative 3rd. We add those exponents. That's going to be 6 plus a negative 3 is 3. So b to the 3rd. And then c to the negative 6th. I'm not doing anything with that yet. And then the denominator, I'm not doing anything with that yet either. Okay, the only things that I have left to do are I have this coefficient over 4. I can simplify those. They're both divisible by 2, so I can go ahead and simplify that. And then also this negative 6, I need to get rid of that negative exponent. So again, we take the reciprocal of the base, which is the c, and then drop the negative. So I'm going to do both of these in one step. 2 goes into 4 twice, and into 270 135 times. So that's going to leave me with still negative out there, negative 135. A to the 9th, b to the 3rd, and then all over 2a squared, and now this is going to be a c to the positive 6. When I take the reciprocal of that base and bring it down, it is positive. Okay, so that's several examples of those different rules. These can get a little tricky, but just kind of take it one step at a time. I think if you try to look at the whole thing at one time, it can get kind of tricky. So like I said, this step, if you have a power, go ahead and apply that unless it's negative on the outside, in which case you can address that negative for the entire portion of the expression, that base. And yeah, that's it. So the next video will be coming up. All right.